Right now, the Andromeda Galaxy is close enough that its outer atmosphere of gas has already reached ours. Two galaxies still 2.5 million light-years apart, already touching at the edges. Subscribe, there's a new one every few days. This is White Space. Settle in. For a long time, astronomers believed they understood the Milky Way's place in the universe. It was assumed to be exceptional. Its structure, a thin spinning disk wrapped inside a thicker, more diffuse one, seemed to mark it as a product of violent history. The thick disk, astronomers argued, was born from catastrophe. A massive collision with another galaxy roughly 9 billion years ago, an event so powerful it scattered ancient stars upward and outward, leaving them suspended above and below the plane like a fossil record of destruction. The Milky Way wore its double disk like a scar. Then, in the constellation of Ophiuchus, they found UGC 138. This galaxy sits about 320 million light-years away, a modest distance by cosmological standards. When high-resolution images came back, astronomers noticed something unexpected. UGC 138 also had two distinct disk components, a thin inner layer and a broader, more diffuse outer layer, strikingly similar in proportion and character to our own. But there was no sign that UGC 138 had ever collided with anything. No disrupted arms, no asymmetric shells, no evidence of a merger in its past. The double disk structure had simply grown that way, a natural outcome of spiral galaxy evolution. The implication is quiet but significant. The Milky Way may not be a survivor of an ancient catastrophe. It may simply be a normal spiral galaxy, one of countless ordinary systems that build double disks as a matter of course. We are not exceptional, we are common. And somewhere in UGC 138, it is possible that the same thought is occurring to someone else. This question, what is normal, what is ordinary, runs through every aspect of galactic astronomy. The history of the discipline is largely a history of dethroning exceptionalism. We learned the Sun was not the center of anything. We learned the Milky Way was not the only galaxy. We learned that our cosmic address was not even a particularly special one within the network of filaments and voids that constitutes the large-scale structure of the universe. UGC 138 is one more lesson in the same direction. The features we thought made us unique turn out to be features we share with objects we have barely begun to study. Galaxies themselves are classified by their morphology, the shape we observe when we image them in visible light. The Hubble tuning fork diagram, introduced by Edwin Hubble in 1926 and still used as a pedagogical framework, arranges galaxies from ellipticals on the left, smooth, featureless, ranging from nearly circular to highly elongated, to spirals on the right, separated into those with and without central bars. Lenticular galaxies, which have disks but no spiral arms, sit at the fork's junction. Irregular galaxies, which resist classification, were placed outside the scheme entirely. The tuning fork was never meant as an evolutionary sequence, though for decades many astronomers treated it as one, imagining galaxies evolving from spirals to ellipticals as they aged. The current understanding is more complicated. Ellipticals are not simply old spirals, but the products of major mergers, systems in which the ordered rotation of two spiral disks was scrambled into the random orbital motion that characterizes elliptical structure. Lenticulars may represent spirals that lost their gas supply without merging, starved into featurelessness by their environment rather than disrupted by a collision. Within the spiral category, the distinction between barred and unbarred spirals also turned out to be less absolute than originally assumed. Surveys in the infrared, where dust which scatters blue light more than red becomes more transparent, revealed bars in galaxies that appeared unbarred in visible light. Andromeda itself may harbor a bar hidden beneath its dust lanes. The Milky Way's bar has been confirmed by infrared surveys. explaining why its central region is not a simple bulge but a boxy, asymmetric structure. Bars are not unusual features. They may be the default configuration of mature spiral galaxies, a natural product of secular dynamical evolution acting over several billion years. To understand what the Andromeda Galaxy actually is, not as a mythological object, not as a distant smudge of light, but as a physical system, we have to start with what surrounds it before we even reach its disk. Every large galaxy is embedded in a vast, nearly invisible atmosphere of diffuse gas. This atmosphere is called a halo, and for most of history it was extremely difficult to study because it emits almost no light detectable by conventional means. The gas is there, it is ionized, meaning electrons have been stripped from their parent atoms by radiation, leaving behind a plasma so thin that millions of particles occupy the space where a single grain of dust would sit. To see it, you have to catch it in the act of absorbing something, and that something turned out to be quasars. Quasars are among the most luminous objects in the observable universe. They are the active cores of distant galaxies, powered by supermassive black holes consuming matter at extraordinary rates. Because they are so far away and so bright, quasars make ideal background light sources, cosmic flashlights that shine through whatever lies between them and us. When their light passes through the halo of Andromeda on its way to our telescopes, the gas absorbs specific wavelengths. By measuring exactly which wavelengths vanish, astronomers can read the halo's composition, temperature, and motion like a fingerprint. The Hubble Space Telescope carried the instrument that made this possible, the cosmic origin spectrograph sensitive to ultraviolet light that never reaches the ground because Earth's atmosphere absorbs it. Using 43 quasars distributed at various angles behind Andromeda's halo. A program known as AMIGA, Absorption Map of Ionized Gas in Andromeda. A team of researchers constructed a three-dimensional map of the gas. What they found surprised even the optimists. Andromeda's halo extends approximately 1.3 million light-years in the direction of the Milky Way. In other directions, it reaches out to nearly 2 million light-years. The distance between Andromeda and the Milky Way is roughly 2.5 million light-years. This means the outer edges of their two halos are already touching. Two galaxies still over 2 million light-years apart are already, in some diffuse sense, in contact. The halo itself is not uniform, it has layers. The inner zone, extending to roughly 500,000 light-years from Andromeda's center, is turbulent and chemically enriched. Astronomers found heavy elements there, oxygen, silicon, carbon elements that can only be forged in stellar interiors and ejected by stellar death. Supernovae drive these metals outward, enriching the halo with the remnants of billions of previous stellar generations. The outer halo, by contrast, is smoother and hotter, more pristine, less disturbed by what happens inside the disk. The boundary between them is not sharp, but the transition is real. This layered structure carries information about the history of feedback, the process by which energy released inside the galaxy propagates outward and shapes the surrounding medium. The inner halo bears the marks of supernovae whose light died out hundreds of millions of years ago. The heavy elements those explosions produced are still suspended in the gas, carried outward by the momentum of the blast and never fallen back. The outer halo retains conditions closer to the primordial, a large reservoir of gas that has not yet been chemically processed by stellar activity, waiting to be drawn inward and converted into the next generation of stars. This gas is not merely a relic, it is fuel. Every galaxy needs a continuous supply of hydrogen to sustain star formation, and the halo represents the reservoir from which the disk draws its raw material over billions of years. Studying the circumgalactic medium, the technical term for this extended halo, has become one of the central preoccupations of modern galaxy formation research. The reason is simple. Models of galaxy formation consistently underpredict how much star formation is suppressed in large galaxies. Something heats the halo gas and prevents it from cooling rapidly enough to rain down on the disk and ignite new stellar generations. The leading candidate is feedback from the central black hole. But the details of how black hole energy couples to halo gas at scales of hundreds of thousands of light years remain poorly understood. Andromeda, close enough to study quasar sightlines through its halo at high resolution, is one of the best natural laboratories for working this out. Moving inward past the halo, past the stellar streams and the outer stellar halo, we reach the disk of Andromeda itself, the main structure, the place where most of the galaxy's mass in ordinary matter resides, the region whose light reaches us as that faint autumn smudge. Andromeda's disk shows something that sets it apart structurally from a simple textbook spiral. A prominent ring-like enhancement in star formation activity at a radius of roughly 32,000 light-years from the center. This feature, sometimes called the 10 kiloparsec ring, is one of the most active zones of star formation in the entire local group. It is visible in infrared images as a bright annular structure glowing with the thermal emission of warm dust heated by embedded young stars. The origin of the ring is debated. It may be a density wave feature, a standing wave in the disk, analogous to a traffic jam that persists even as individual stars pass through it, or it may be the result of a head-on collision with a smaller companion galaxy, which would have sent a concentric ring of compressed gas propagating outward like a ripple on a pond. The candidate responsible for this collision, if collision it was, is Andromeda's compact satellite M32. Simulations show that if M32 passed nearly directly through Andromeda's disk several 100 million years ago, it would have generated a ring of compressed star-forming gas at roughly the observed radius. M32 itself would have lost mass in the encounter, which is consistent with its current appearance as a stripped remnant galaxy. The ring, in this interpretation, is the wound left by that ancient impact. A permanent scar in the star-forming pattern of a galaxy that is otherwise still healing. Beyond the ring, Andromeda's outer disk shows further distortions. The northeastern spiral arm, which extends outward from the 10 kiloparsec ring, is kinematically unusual. Its stars do not follow the expected rotation pattern, but show significant velocity perturbations consistent with a past or ongoing interaction. The outer disk as a whole is warped, tilted out of the inner disk plane, which again points to gravitational perturbations from the satellites orbiting around it. In the stellar halo of Andromeda, extending far beyond the disk and distinct from the gaseous halo mapped by Hubble, astronomers have found an extraordinary network of stellar streams. These are long, coherent arcs and ribbons of stars distributed across hundreds of thousands of light years, each representing the remains of a smaller galaxy that came too close to Andromeda and was torn apart by tidal forces. The most prominent of these is the giant stellar stream, a river of stars that stretches nearly 300,000 light years from Andromeda's center. Its progenitor galaxy, whatever it was, no longer exists as a recognizable structure. Its stars have been unraveled and redistributed along the orbit that the original system once followed. By measuring the velocities and metallicities of the stars in the stream, astronomers can reconstruct the history of the event. When the progenitor fell in, how massive it was and what its orbit looked like. The giant stellar stream is one of the most complete tidal disruption events known in any nearby galaxy, a record of an entire galaxy's destruction preserved in stellar debris. Approaching the disk of Andromeda, the first thing a traveler would notice is the spiral arms. They are real structures, regions of enhanced density where gas compresses and collapses into new stars. But they are not the smooth geometric arcs that diagrams suggest. They twist, they fragment. In places they appear kinked or broken, as though something large passed through them at high speed. Several of those distortions are genuine impact scars. Over the past several billion years, Smaller satellite galaxies have plunged through Andromeda's disk like stones dropped through still water, sending ripple patterns across the spiral structure that persist for hundreds of millions of years after the event. The arms connect outward from the bulge, the central spheroidal concentration of mostly older, redder stars that forms the bright heart of the galaxy. Andromeda's bulge has long been classified as a classical smooth structure, but infrared observations conducted under the 2MAS survey revealed something hidden beneath the dust. The bulge appears slightly boxy when viewed in infrared light. A boxy bulge almost always indicates the presence of a bar, a linear structure linking the bulge to the spiral arms, similar to the one that defines our own Milky Way as a barred spiral. Whether Andromeda hosts a true bar remains an open question, but the structural similarity to our galaxy grows whenever we look in wavelengths that see past the dust. Andromeda contains roughly 1 trillion stars. The number is almost meaningless on a human scale, but it has a physical consequence. More stars means more of everything. More variable stars, more stellar remnants, more interaction between systems, more opportunities for unusual configurations to arise. Within Andromeda's disk, astronomers have catalogued over 35,000 variable stars, objects whose brightness changes with time. The most cosmologically important among them are Sepphide variables, stars that pulsate with a rhythm precisely tied to their intrinsic luminosity. Measure the period and you know the true brightness. Compare that to the apparent brightness as seen from Earth, and you have the distance. It was Cepheids in Andromeda that Edwin Hubble used in 1923 to prove the galaxy lay far beyond the boundaries of the Milky Way. Before that observation, the debate over whether spiral nebulae were nearby gas clouds or independent stellar systems had lasted decades. Hubble's measurement, placing Andromeda at around 900,000 light-years, somewhat short of the modern value of 2.537 million, but unambiguously outside our galaxy, ended the debate. The universe was not the Milky Way. The Milky Way was one island in an ocean of islands, in addition to classical Cepheids, massive luminous pulsators cycling over periods of days to months. Andromeda hosts several other classes of variable stars that each probe different aspects of stellar physics. RR, Lyrae variables are old low-mass stars crossing the instability strip of the Hertzsprung-Russell diagram in a late evolutionary phase. They pulsate with periods shorter than 1 day. And because they are intrinsically faint, their detection in Andromeda requires the most sensitive instruments available. But their presence is invaluable. RR Lyrae stars trace the oldest stellar populations. The galaxy's original stellar content formed in the first few billion years after the Big Bang. Their distribution in the halo of M31 maps the ancient skeleton of the galaxy before it had assembled its current disk. Long-period variables which pulsate over cycles of hundreds of days trace the other end of stellar evolution. Evolved giant stars in the last stages of their lives, swollen to hundreds of times the sun's diameter, shedding their outer layers in slow stellar winds. These are the Mira-type variables named after the prototype Mira in the constellation Cetus, a red giant visible to the naked eye at peak brightness, but fading to invisibility at minimum. In Andromeda, populations of long-period variables have been mapped using near-infrared surveys that cut through the dust obscuring the disk. Their period distributions reveal the age and chemical composition of the stellar populations they trace. Luminous blue variables, massive, unstable stars that occasionally shed their outer layers in traumatic eruptions appear in the disk of M31 as well. The prototype of the class in our own galaxy is Eta Carinae, which in 1843 underwent a great eruption that temporarily made it the second brightest star in the sky, despite lying 7,500 light-years away. The analogous stars in Andromeda are too faint to see individually without large telescopes, but they can be identified by the nebulae they create as they expel material, and by the characteristic spectrum of their outbursts. Each one is a stellar system on the edge of stability, a star so massive that its own luminosity nearly exceeds the gravity holding it together, with the balance tipping periodically into eruption. The galaxy also produces around 50 novae per year, binary systems in which a white dwarf accretes hydrogen from a companion until the surface ignites in a thermonuclear flash. More than 800 nova outbursts have been recorded in M31. This rate, normalized against the galaxy's total luminosity, is actually somewhat low, consistent with a galaxy that has been forming stars more slowly in recent epochs and therefore has a smaller population of young, short-lived binary systems. The nova rate is a quiet diagnostic, a way of measuring star formation history not by looking at the stars themselves, but by counting their deaths. Deeper still, Andromeda contains over 2,000 detected X-ray sources. Most are X-ray binaries, systems where a compact object, either a neutron star or a black hole, strips material from a normal stellar companion, heating the accreted gas to temperatures at which it emits energetic radiation. Others are the remnants of supernovae, expanding shells of gas that still glow in X-rays tens of thousands of years after the original explosion. Globular clusters in Andromeda are particularly prominent X-ray emitters, more so than their counterparts in the Milky Way, hinting at differences in the binary populations within these dense stellar environments. Among the most energetic X-ray sources in M31 are a class of objects called ultraluminous X-ray sources, or ULXs. These systems emit more X-ray energy than can be produced by a stellar mass black hole accreting at its theoretical maximum rate. Their nature has been debated for decades. Some appear to be neutron stars accreting at super Eddington rates, that is, accreting faster than the simple photon pressure limit would allow through poorly understood geometries or magnetic field effects. Others may be intermediate mass black holes, objects of hundreds or thousands of solar masses that occupy the gap between stellar mass black holes and the supermassive variety at galactic centers. If they are, they represent a population of objects whose formation history is unclear, possibly the remnants of the first generation of massive stars formed in the early universe, or the products of runaway stellar mergers in dense star clusters. The X-ray study of Andromeda conducted with the XMM Newton satellite identified 63 discrete X-ray sources in the central region alone. 46 were classified as X-ray binary systems. The remainder included neutron stars, black hole candidates, and objects whose classification remains uncertain. This catalog represents one of the most complete X-ray surveys of a nearby galaxy nucleus, providing a census of the compact object population that would be impossible to obtain for more distant systems. We move now to the center. The bulge of Andromeda, seen through Hubble's instrument's invisible light, is a crowded, brilliant region. But at its heart lies something that requires more than ordinary attention. The central 100 light-years of M31 contain a configuration of objects unlike anything seen at comparable proximity. There are young blue stars, not old stars of the bulge, but genuinely young objects, no more than 200 million years old, orbiting directly around the galactic center. Their orbits are compact and regular, like a miniature planetary system scaled to stellar masses. This is deeply strange. Young massive stars are voracious. They consume their hydrogen fuel in a few million years at most. For them to exist this close to the galactic center, they must have formed there, not drifted in from somewhere else, because there would not have been time. But forming close to a supermassive black hole is normally impossible. The tidal forces near a massive compact object shear apart any gas cloud before it can collapse under its own gravity, preventing star formation in a zone that should be sterile. Andromeda's blue stars formed there anyway. How they did it remains one of the outstanding questions of galactic astrophysics. One idea is that a dense molecular gas cloud somehow became gravitationally unstable despite the tidal environment, producing a rapid burst of star formation before the surrounding forces could disrupt it. Another is that a star cluster migrated inward from a slightly larger radius, dragged by dynamical friction against the background stellar population. Neither explanation is fully satisfactory. The stars are there, and we are still working out why. The nucleus of Andromeda is more complex than it first appears in imaging. Careful analysis of high-resolution Hubble data resolved the central region into three distinct components, designated P1, P2, and P3. P1 and P2 are the two apparent brightness peaks of what was originally called the double nucleus, the offset concentrations of all the red stars whose apparent separation gave rise to years of speculation about binary nuclei. P3 is the smaller, bluer concentration at the true dynamical center, the concentration of young stars orbiting the supermassive black hole at the very heart of the system. Each component has a distinct stellar population, a distinct age, and a distinct dynamical history. Disentangling them required photometric and spectroscopic observations spread over multiple observing campaigns with multiple instruments. Surrounding these young stars in P3 is the double nucleus structure formed by P1 and P2, perhaps the most discussed structural feature in M31's center. The apparent double peak is likely not two separate clusters at all, but a single ring of old red stars seen edge-on or at an oblique angle, because stars in an elliptical orbit spend more time near the far end of their path, where they move slowest. The ring appears brighter at two opposite sides, creating the illusion of two separate concentrations. The ring itself orbits the central black hole at a distance of roughly 5 light-years. Within it lies the disk of young blue stars. The two structures appear to share a common orbital plane, which suggests they formed through related physical processes rather than separately. At the very center of all this is the black hole itself. The supermassive black hole in M31 carries a mass of approximately 100 to 140 million times the mass of the Sun. For comparison, the black hole at the center of the Milky Way, Sagittarius A, is about 4 million solar masses. Andromeda's central black hole is roughly 30 times more massive. Its event horizon, the boundary beyond which nothing, including light, can return, is too small to resolve with current instruments. But its influence extends across thousands of light-years, shaping stellar orbits, modulating gas flows, and setting the pace of star formation in the nuclear region. The mass was determined by measuring the velocities of stars orbiting near the center. Stars moving in tight orbits at high speeds reveal the mass of whatever lies at the center of those orbits. This is the same principle by which we weigh a star by watching a planet orbit it, except here the planet is a massive star, and the star at the center is a black hole 30 times the mass of the Milky Way's own. Unlike Sagittarius A, which despite its mass is currently among the least active supermassive black holes known, its X-ray luminosity is far below what accretion at even a modest rate would produce. The Andromeda black hole shows slightly more activity. X-ray observations have detected a faint but persistent nuclear X-ray source consistent with a low-level accretion process. Occasionally, objects pass close enough to the black hole to be disrupted by tidal forces before they can escape, producing brief flares of X-ray emission called tidal disruption events. Several candidate tidal disruption events have been identified in archival X-ray data for M31. In each case, a star, or in some cases a dense gas cloud, approached the black hole closely enough that the tidal forces across the object exceeded the object's own self-gravity, pulling it apart. The resulting stream of material spirals inward, forming a temporary accretion disk that radiates intensely in X-rays for months before fading as the fuel supply is exhausted. These events are rare, perhaps one per galaxy per 10,000 to 100,000 years, but by surveying many galaxies stypnagically, astronomers have built a catalogue of several hundred confirmed or suspected cases. They probe the physics of accretion under extreme conditions and provide a way to detect otherwise quiescent black holes through their brief episodes of stellar consumption. Andromeda hosts approximately 460 confirmed globular clusters, dense spherical concentrations of stars that formed early in the galaxy's history and survive as gravitationally bound systems today. The most massive known cluster in the local group is Mayal 2, also designated G1, located about 130,000 light-years from Andromeda's center. It contains roughly 300,000 stars, mostly old metal-poor objects from the galaxy's earliest epochs. Its luminosity exceeds that of any globular cluster in the Milky Way by a significant margin. G1 is particularly intriguing because its internal stellar population suggests it may not be a true globular cluster at all, but rather the stripped nucleus of a small galaxy that Andromeda absorbed long ago. The cluster shows evidence of multiple stellar generations, stars of different ages and chemical compositions that seem to have formed in distinct bursts rather than simultaneously, the signature of a system with its own protracted star formation history before being tidally stripped down to its compact core. At its center sits a black hole candidate of approximately 20,000 solar masses, intermediate between the stellar mass black holes that form from collapsing individual stars and the supermassive black holes anchoring galactic nuclei. The globular cluster system of Andromeda is itself a record of the galaxy's formation history. Globular clusters are among the oldest objects in any galaxy. Their stars typically formed in the first few billion years of cosmic time, during the rapid burst of star formation that accompanied the initial collapse of the galaxy's progenitor clouds. The chemical composition of their stars, specifically how much iron and other heavy elements they contain relative to hydrogen, reflects the state of galactic chemical enrichment at the time of their formation. Metal-poor clusters formed earliest, when the galaxy had not yet been enriched by stellar nucleosynthesis. Metal-rich clusters formed later in a more chemically mature environment. Andromeda's globular cluster system shows a clear metallicity bimodality, a blue metal-poor population and a red metal-rich population, roughly corresponding to clusters formed in the early universe and those formed in a later, more chemically enriched phase. This bimodality is a generic feature of massive galaxy globular cluster systems. Its origin is still debated. The two populations may represent clusters formed in two distinct episodes of star formation within the same galaxy. Or the metal-poor population may have been accreted from smaller satellite galaxies absorbed over cosmic time, while the metal-rich population formed in situ in the host galaxy's disk. Beyond the classical globular clusters, astronomers have identified an entirely new class of stellar systems in Andromeda's halo. These objects are as populous as globular clusters, containing hundreds of thousands of stars, but extend over hundreds of light years in diameter rather than tens. They are more diffuse, less massive per unit volume, and have no obvious counterpart among Milky Way structures. They appear to occupy an intermediate position between globular clusters and dwarf spheroidal galaxies, raising questions about whether these categories are as distinct as previously assumed. Some may be the expanded remnants of dissolved dwarf galaxies, others may represent a mode of star cluster formation that simply does not occur in our own galaxy's environment. As for planets, only one confirmed exoplanet candidate has been detected in M31, the object designated PA99N2, found through microlensing. The technique detects planets by watching for the brief brightening of a background star as an intervening planetary system passes in front of it, its gravity acting as a lens. BA99N2 remains unconfirmed without independent verification. But by any statistical reasoning, a galaxy containing 1 trillion stars almost certainly contains billions of planetary systems. The question of what orbits those stars, whether any of those worlds maintain liquid water, whether any have generated the kind of chemical complexity that preceded life here, is one we cannot answer yet. The tools to answer it do not yet exist for objects at Andromeda's distance, but they are being built. Andromeda is not alone. It is attended by a court of smaller galaxies that orbit it, interact with it, and in some cases are slowly being absorbed by it. 2 satellites are visible in almost any amateur photograph of M31. M32 and M110 appear as companion patches of light flanking the main disk. M32 is classified as a compact elliptical galaxy, a type so rare that it may represent its own distinct formation pathway. Current evidence suggests M32 was once a larger spiral galaxy whose outer disk was stripped away by Andromeda's tidal forces over billions of years, leaving only the dense inner bulge. The interaction that transformed M32 also disturbed it. Andromeda's tidal field suppresses the formation of spiral arms in M32 and drives an ongoing exchange of stars between the 2 systems. Muftenes Twens, formerly NGC 205, is a dwarf elliptical galaxy considerably more extended than M32 and showing signs of active star formation in its central region, a blue stellar population young enough to count as ongoing rather than historical. This is unusual for a small elliptical galaxy which typically exhausted its gas reservoir long ago. The explanation likely involves Andromeda's gravitational influence, which may have triggered a minor burst of star formation by compressing gas in M. Muften-Den's nucleus. Less photographed but equally important are 2 other Andromeda satellites, NGC 147 and NGC 185. Both are dwarf elliptical galaxies lying at distances of approximately 2 million light-years from Earth, which places them in the general vicinity of M31 and marks them as likely members of its satellite system. NGC 105 contains a small amount of dust and gas at its center, unusual for an elliptical galaxy of this size, and shows evidence of relatively recent star formation, making it similar in character to M110. NGC 147 is more purely an old stellar system with little ongoing star formation and a smooth, featureless appearance. Together, the 4 bright satellites of Andromeda, M32, M1000, NGC 147 and NGC 185 form the inner retinue around which dozens of smaller, fainter companions are distributed. Those fainter companions number in the dozens. They carry designations from Andromeda I through Andromeda XXeV and beyond, catalogued incrementally as progressively deeper imaging surveys have revealed increasingly faint stellar systems. Many are dwarf spheroidal galaxies, objects so faint and diffuse that they contain very little gas, few young stars, and are held together primarily by dark matter, rather than by the gravity of their visible stellar mass alone. Several have effective surface brightnesses so low that they were invisible in photographic surveys and were only discovered through automated detection algorithms applied to digital sky surveys, capable of detecting overdensities of stars spread across square degrees of sky. These ultra-faint dwarfs are among the most dark matter-dominated objects known. In some of them, the mass of dark matter exceeds the mass of visible stars by factors of hundreds or thousands. They are, in a sense, galaxies that barely formed systems where dark matter pooled in gas and triggered just enough star formation to produce a handful of old metal-poor stars before the process shut down, either because the gas supply was exhausted or because the ultraviolet background of the early universe evaporated the remaining gas before it could collapse. They preserve chemical and dynamical information about conditions in the early universe, in a form that massive galaxies with their long histories of star formation and chemical enrichment have long since overwritten. One curious geometric feature of Andromeda's satellite system deserves particular attention. When the positions of the bright satellite galaxies around M31 are mapped in 3 dimensions, they do not appear to be distributed randomly around the host galaxy. Instead, they are preferentially arranged in a vast, thin plane, a co-rotating disk of satellites that has been called the Great Plane of Andromeda. Roughly half of Andromeda's known bright satellites share a common plane extending to hundreds of thousands of light years from the galactic center, and many of those satellites appear to be orbiting in the same sense within that plane, as though they share a common origin or orbital heritage. This coplanar arrangement is not easily explained by standard cosmological models. In simulations of galaxy formation based on cold dark matter, satellite galaxies are expected to be distributed in roughly isotropic configurations around their host, coming in from all directions, reflecting the isotropic distribution of dark matter substructure. Finding that Andromeda's satellites are coplanar and co-rotating suggests that either the standard model is missing something, or that the satellite plane arose from a specific past event. Perhaps a group of smaller galaxies that fell into the local group together along a common filament and were captured by Andromeda's gravity as a coherent ensemble rather than as individually accreted objects. The resolution of this tension between observation and simulation is still ongoing. Now comes the future. In approximately 4 billion years, Andromeda and the Milky Way will collide. The outcome of that collision has been calculated in increasingly fine detail over the past 2 decades, using n-body simulations that track hundreds of millions of particles under mutual gravity. The results are consistent. The merger is inevitable. It will be prolonged, and it will be violent in the way that cosmic processes are violent, not a single instant of destruction, but a centuries-long gravitational drama playing out across hundreds of millions of years. The first approach will not be a clean impact. The 2 galaxies will sweep past each other like 2 waves passing through the same water, their stellar populations interpenetrating rather than colliding. Stars are so widely separated that the chance of any 2 stars from opposite galaxies actually striking each other is essentially 0. What does happen is gravitational. As the galaxies pass, they distort each other. Stars are flung onto new orbits. Long tidal tails of stripped material stream outward. The disks lose their spiral structure as the orbits that maintained it are disrupted. After the first pass, the 2 systems will not continue apart indefinitely. Gravity will pull them back. A second pass will follow the first, even more disruptive than the first contact. Eventually, after multiple encounters spanning perhaps 1 billion years from first contact to final merger, the 2 galactic centers will spiral together and merge. 2 supermassive black holes, Andromeda's 100 million solar mass object and the Milky Way's 4 million solar mass Sagittarius A, will form a gravitational binary, losing energy through gravitational wave emission and dynamical friction until they merge into a single more massive black hole. The merger will not merely rearrange stars, it will also rearrange gas. Both galaxies still retain significant reservoirs of interstellar gas in their disks, the raw material for star formation. When the 2 disks interpenetrate, gas clouds from one galaxy will collide with gas clouds from the other at velocities of hundreds of kilometers per second. These collisions are not like stellar collisions. Gas is collisional, meaning clouds interact directly rather than passing through each other. The kinetic energy of the impact is converted into thermal energy, heating the gas, and into turbulent energy, compressing it on multiple scales simultaneously. The result is a burst of star formation, a period during which new stars form at rates far exceeding the normal pace in either galaxy. This starburst phase, triggered by the merger, could produce hundreds of times more stars per year than the current quiescent rate in the Milky Way. The newly formed stars will be predominantly blue and massive, lighting the merged system with the fierce, short-lived glow of O and B-type stars. Their deaths as supernovae will drive winds of gas outward, enriching the halo with newly forged heavy elements. After perhaps 100 million years, the burst will be over. The available gas will have been largely consumed or expelled. The most massive stars will have died. What remains will be a steadily aging population of less massive, longer-lived stars. The remnants of the merger-induced burst slowly cooling as the galaxy transitions to quiescence. Simulations of the Milky Way-Andromeda merger predict that the interaction will also affect the satellite galaxies of both systems. Some satellites will be flung outward into wide orbits around the merged remnant. Others will be drawn inward and stripped. The Magellanic Clouds, if they survive on their current trajectory until the merger begins, will be significantly perturbed by the encounter. Their fate depends sensitively on their orbital parameters at the time of the merger, parameters that are themselves still being refined by measurements of their proper motions using Hubble and Gaia observations. What will the sky look like? About 3.5 billion years from now, as the first approach begins, Andromeda will have resolved into visible structure from Earth. Its central bulge will have brightened. Individual stellar associations along its arms will be distinguishable. The galaxy will span an angular diameter comparable to the full moon's, but extending further with increasing exposure. The night sky will hold a second sprawling object beside the moon, not the compact fuzzy patch visible today, but something with visible interior structure, faintly spiral, brightening toward its core. As the merger progresses, the Milky Way's own disk will be disrupted. The band of light we call the Milky Way will gradually fragment and distort. Millions of years later, it will no longer exist as a coherent band. The sky will grow brighter, not from light but from stars, as the density of nearby stellar systems increases. New regions of star formation, triggered by the compression of gas clouds during the merger, will light distant parts of the combined system with blue stellar nurseries. The most likely fate of our Sun during this process is continued survival. The probability of the solar system experiencing a direct stellar encounter, another star passing close enough to perturb planetary orbits significantly, remains small even during the merger. However, simulations estimate roughly a 12% chance that the solar system will be scattered out of the disk during the first passage. A 3% chance exists that it will be captured into Andromeda's potential, well, rather than remaining in the Milky Ways. Both outcomes are survivable for the planetary system itself. The greater threat to any hypothetical future inhabitants of Earth is the Sun's own natural evolution, its gradual brightening as it ages, and its eventual expansion into a red giant, which will occur on roughly the same time scale regardless of what the surrounding galaxy is doing. The merged remnant of the Milky Way and Andromeda will not be a spiral galaxy. It will be an elliptical, a large featureless system of old stars, slowly exhausting its remaining gas reservoir and forming fewer and fewer new stars as the centuries accumulate. The blue arms and pink star-forming regions will fade. What remains will be a smooth red oval of aging stellar populations, billions of years old, orbiting a central black hole that is itself the product of two ancestors. The new galaxy has informally been called Milkomeda by some astronomers, a portmanteau that loses something in dignity but captures the essential reality. Two galaxies, two lineages, one combined future. But Andromeda and the Milky Way are not the largest systems their kind has produced. Elsewhere, in the observable universe, galaxies have grown to dimensions that make even M31 look modest. To understand scale, it helps to start with a reference. The Milky Way spans roughly 100,000 light-years from edge to edge. Andromeda stretches to perhaps 220,000 light-years. These numbers feel large, they are large. And then there is Hercules A. Hercules A, also designated 3C 348, is a radio galaxy sitting approximately 2 billion light-years away. Its stellar disk extends to roughly 1.5 million light-years across, 15 times the diameter of the Milky Way. Its central black hole exceeds 1 billion solar masses, roughly 1,000 times more massive than Andromeda's. Hercules A is also one of the most powerful radio sources in the extragalactic sky, producing twin jets of plasma that extend hundreds of thousands of light-years from its nucleus. These jets carry material ejected from the accretion disk around the central black hole, and where they terminate, they inflate enormous lobes of radio-emitting plasma. Larger still is IC 1101, a supergiant elliptical galaxy at the center of galaxy cluster Abell 2029, roughly 1.04 billion light-years distant in the constellation Virgo. IC 101 reaches a diameter of approximately 6 million light-years, 60 times the Milky Way. Its total mass is estimated at roughly 100 trillion solar masses, perhaps 2,000 times the mass of our own galaxy. If IC 1101 were positioned where the Milky Way currently sits, it would extend past the Magellanic Clouds, past Andromeda, and nearly to the Triangulum Galaxy. It would engulf the entire local group. IC 1101 reached these dimensions through accumulation, a long history of absorbing smaller galaxies over billions of years. It sits at the gravitational center of its cluster, where smaller systems fall inward and merge. The galaxy is composed predominantly of old red stars, having largely exhausted its gas supply and slowed its star formation. To maintain its size, it must continue absorbing external material. It is, in a sense, still growing. Further along the size scale is UGC 9555, a radio galaxy in the direction of the constellation Camelopardalis, about 820 million light-years away. Its diameter exceeds 8 million light-years. Estimating its mass is challenging at these distances, but current assessments place it in the tens of trillions of solar masses. Like most of the largest known galaxies, it grew by consuming its neighbors in a dense cluster environment. Then there is 3C236. This radio galaxy, located in the constellation Leo Minor, holds one of the largest measured extents of any radio structure in the universe. Its radio-emitting lobes, produced by twin jets from a central active nucleus, stretch to approximately 15 million light-years from tip to tip. The host galaxy itself is more compact than its radio emission, but the jets it produces trace a volume of space larger than the local group. And at the summit, as of current observational records, is Alcyoneus. Alcyoneus is a radio galaxy located approximately 3 billion light-years from Earth. Its radio lobes extend to more than 16 million light-years in total length, making it the largest known structure produced by a single galaxy. The discovery was made using LOFAR, the low-frequency array, a European network of over 20,000 radio antennas distributed across 52 stations. LOFAR detects low-frequency radio emission that no single conventional telescope could capture. By processing data from antennas separated by hundreds of kilometers, the network achieves the resolving power of a telescope thousands of kilometers in diameter. Alcyoneus is not especially unusual in its black hole mass, its host galaxy luminosity, or its jet power. By the ordinary metrics by which radio galaxies are characterized, it is unremarkable. This is precisely what makes it interesting. Whatever drove Alcyoneus to its extraordinary size? whether it is the low density of the environment through which its jets propagate, or an unusually stable configuration of the magnetic field that constrains them, or simply a matter of age. The galaxy, having had an exceptionally long, uninterrupted jet-active phase, the cause is not yet identified. The researchers involved in the discovery note that Alcyoneus appears to still be expanding. It has not reached whatever limit, if any, eventually constrains these structures. What Alcyoneus and Hercules A and 3C236 share is the central mechanism, a supermassive black hole, an accretion disk, and a pair of jets. The jets emerge perpendicular to the disk plane, confined by magnetic field lines wound around their axis, accelerating plasma to close to the speed of light over distances of thousands of light years before the jet structure begins to broaden and decelerate. The transition from a confined relativistic jet to a diffuse subrelativistic plume marks the point at which the jet begins to interact strongly with the surrounding intergalactic medium. At that transition, the jet's kinetic energy is partially converted into thermal energy in the surrounding gas, and partially into the magnetic field energy of the radio lobe. The electrons in the lobe emit synchrotron radiation, radio waves produced when relativistic electrons spiral around magnetic field lines. This is the radio emission that makes radio galaxies detectable across billions of light years. Over time, the electrons in the lobe lose energy through this radiation and through inverse Compton scattering with photons of the cosmic microwave background. The lobe ages, its radio emission fading first at high frequencies and last at low frequencies. LOFA sensitivity at low frequencies is what allows it to detect the most extended and oldest radio lobes, structures too faint to see at higher frequencies but still glowing faintly in the kilohertz range. This emission at such low frequencies is also why Alcyoneus' enormous lobes were only recently discovered, despite being the largest known structure of their kind. Earlier surveys at higher radio frequencies had seen the core of the galaxy but missed the full extent of its aged, fading lobes. Only with LOFA's combination of low frequency sensitivity and angular resolution, achieved through its continental baseline, did the complete picture emerge. The mechanism connecting all of these giants IC111, Alcyoneus, Hercules A, is the supermassive black hole at their centers, and the interplay between that black hole and the surrounding matter. In any large galaxy, the central black hole is not merely a passive object lurking at the center. It is an active participant in the galaxy's evolution. Material falling toward the black hole forms an accretion disk, a flat rotating structure of compressed and heated gas that glows across the electromagnetic spectrum. The inner regions of this disk, where temperatures reach tens of millions of degrees, emit X-rays. The outer regions, somewhat cooler, emit infrared and optical light. The entire structure can outshine the rest of the galaxy by orders of magnitude when the accretion rate is high, producing a quasar. As material accretes, the disk generates a magnetic field. That field, interacting with the rotating black hole, launches jets, narrow beams of plasma, electrons, and magnetic field lines perpendicular to the disk plane, accelerating particles to nearly the speed of light. These jets carry kinetic energy out of the galactic nucleus at enormous rates. When they terminate, when they finally slow to subrelativistic speeds in the surrounding intergalactic medium, they inflate the radio lobes that make radio galaxies visible across billions of light years. The jets do something else as well. By depositing energy into the hot gas surrounding the galaxy, they prevent that gas from cooling and collapsing to form new stars. This process, called AGN feedback, for active galactic nucleus feedback, is one of the primary mechanisms by which galaxies shut down their own star formation. A galaxy that produces jets is, in a sense, throttling itself, using the energy of its central black hole to suppress the very process that creates new stellar population. The largest elliptical galaxies, old red star formation suppressed, are the legacy of this process acting over cosmological timescales. In younger galaxies, where star formation proceeds vigorously and the interplay between black hole and disk is still active, the relationship is more complicated. The merger of two gas-rich galaxies can drive massive inflows of material toward the central black hole, triggering an episode of intense accretion. The resulting energy output through jets, radiation, and wind scans simultaneously heat the surrounding gas while also compressing other gas clouds, triggering star formation in different regions. The outcome depends on the geometry, the gas density, and the specific properties of the black hole involved. In some mergers, this process has been observed directly. In the system IRIS F23128-5919, two gas-rich galaxies are currently merging. Their combined central black holes are accreting furiously. Enormous flows of gas and dust are being expelled from the nuclear region at hundreds of kilometers per second, driven outward by the radiation pressure and mechanical power of the active nucleus. Embedded within those outflows, astronomers have detected young stars, objects tens of millions of years old, clearly formed within the outflow itself, rather than in the quiescent disk. The discovery confirmed that AGN-driven outflows can trigger star formation in the material they expel, creating stars in regions and configurations that would never exist without the black hole's influence. Alongside the black hole, there is a second invisible actor, dark matter. In 1933, the Swiss-American astrophysicist Fritz Zwicky was studying the Coma cluster, a dense collection of galaxies about 320 million light-years away. He measured the velocities of individual galaxies within the cluster and found that they were moving far too fast. The total visible mass of the cluster, all the stars and gas, was insufficient by a large factor to gravitationally confine these galaxies. At the velocities he measured, the galaxies should have been flying apart. They were not. Something unseen was holding them together. The same discrepancy appears within individual galaxies. Stars at the outer edges of spiral galaxies orbit with speeds comparable to stars near the center, when by simple Newtonian reasoning they should orbit much more slowly. The same way outer planets in the solar system move more slowly than inner ones. The rotation curves of galaxies are flat when they should decline. Vera Rubin and Kent Ford, working systematically through the mid-1970s with improved spectrographs at Kitt Peak Observatory, confirmed this behavior for dozens of spiral galaxies. In each case, the outermost measurable stars moved at velocities consistent with a total mass several times greater than the visible stellar mass. The excess gravitational pull that produces these flat curves is attributed to a halo of dark matter surrounding each galaxy, invisible to electromagnetic observation, detectable only through gravity. An independent and powerful confirmation of dark matter's reality came from gravitational lensing. Einstein's general theory of relativity predicts that massive objects bend the path of light passing near them. A galaxy cluster, with its enormous mass, acts as a gravitational lens for background objects, bending and distorting their images into arcs and rings. By measuring the degree of distortion, astronomers can calculate the total mass of the lensing cluster, visible and invisible combined. These measurements consistently show that galaxy clusters contain far more mass than their visible content implies, by factors of 5 to 10. The invisible component is distributed differently from the visible gas and stars, concentrated more smoothly and extending to larger radii. The most striking evidence came from observations of the Bullet Cluster, two galaxy clusters that collided roughly 150 million years ago. The hot gas in each cluster, which constitutes most of the visible mass, interacted during the collision and was slowed by electromagnetic pressure, becoming displaced from the galaxies and dark matter in each system. Gravitational lensing maps of the bullet cluster show clearly that most of the mass is concentrated around the galaxies and their associated dark matter, which passed through the collision without significant interaction, not around the hot gas, which was decelerated. The separation between where the mass is and where the gas is provides direct evidence that the majority of the cluster's mass is in a form that does not interact electromagnetically. It is, by elimination and by positive gravitational evidence, dark matter. Simulations of galaxy formation that include dark matter halos reproduce the observed structures with remarkable fidelity. Galaxies form at the intersection of dark matter filaments, the cosmic web, where dark matter concentrations act as gravitational seeds for the accumulation of ordinary gas, the collapse of that gas into stars, and the eventual assembly of galactic disks and bulges. Remove dark matter from the simulation, and the structures that form look nothing like what we observe. Included in the right proportions, with the right clustering properties, and the simulated universe resembles the real one in remarkable detail. Dark matter and the central black hole together constitute the structural skeleton of a galaxy. The black hole regulates internal processes, star formation, gas circulation, feedback, while dark matter provides the gravitational scaffolding within which the entire visible system operates. The galaxy we see is, in a real sense, only the luminous part of a much larger dark structure. Most of the mass in Andromeda, in the Milky Way, and in every galaxy we have studied is invisible. Let us now take a wider view and consider the neighborhood in which Andromeda and the Milky Way exist. The local group is the name given to the gravitationally bound collection of galaxies to which both belong. It is not a rich cluster. It does not contain thousands of galaxies. It is a relatively modest assemblage spanning approximately 3 million light-years, dominated by two large spiral galaxies, the Milky Way and Andromeda, and attended by dozens of smaller systems of varying types. The closest galaxy to the Milky Way is not Andromeda. It is the Canis Major Dwarf, a disrupted system discovered in 2003, where astronomers noticed an unusual concentration of red giant stars in the constellation of the Great Dog. The Canis Major Dwarf lies approximately 25,000 light-years from the Sun, closer than the galactic center, and is currently being shredded by the Milky Way's tidal forces. Its stars have been drawn into a complex ring-like structure, the Monoceros ring, that wraps around the Milky Way multiple times. The Canis Major Dwarf no longer exists as a coherent galaxy. It exists as a stream of stars in the process of being incorporated into the Milky Way's outer disk, a process that may have been ongoing for billions of years and contributed material to structures we observe today. The next nearest significant systems are the Magellanic Clouds. The Large Magellanic Cloud and the Small Magellanic Cloud, visible to the unaided eye from the southern hemisphere as detached pieces of the Milky Way's disk. The Large Magellanic Cloud sits about 160,000 light-years away, the small about 200,000 light-years. Both are classified as irregular dwarf galaxies, their structures distorted by tidal interaction with each other and with the Milky Way. The Large Magellanic Cloud is the site of the closest observed supernova in nearly 4 centuries, SN 1987A, which exploded in February 1987 in the Tarantula Nebula region. The explosion was visible to the naked eye and provided an unprecedented opportunity to study the early stages of a core collapse supernova in real time. SN Mononotoexismet Ape remains one of the most studied objects in astrophysics. Its expanding shockwave, its neutron star remnant, and the ring structure of material ejected in earlier mass loss episodes are still being monitored by ground and space-based telescopes decades later. The Large Magellanic Cloud also contains the Tarantula Nebula itself, the most active star-forming region in the local group. Formerly designated 30 Doradus, it hosts a massive cluster of young stars called R136, which contains some of the most luminous and massive stars known. Several stars in R136 exceed 100 solar masses, and at least one, R136A1, has been measured at around 200 solar masses, approaching or exceeding what was once thought to be the theoretical upper limit on stellar mass. These stars live for only a few million years before exploding as supernovae, and their presence in such numbers and at such proximity makes 30 Doradus an irreplaceable natural laboratory for studying massive star formation, stellar feedback, and the physics of nebulae lit by ultraviolet radiation far more intense than anything in the Milky Way's disk. Both Magellanic Clouds are connected to the Milky Way by the Magellanic Stream, a long bridge of neutral hydrogen gas that trails behind the clouds as they orbit the Milky Way, extending nearly halfway around the sky. The stream contains no stars, only gas, suggesting it was stripped from the clouds by ram pressure as they move through the Milky Way's halo and by gravitational tidal forces. The outer disk of the Milky Way shows a warp, a deviation from perfect flatness that is attributed in part to gravitational perturbations from the Magellanic Clouds over billions of years. A persistent question about the Magellanic Clouds is whether they are long-term Milky Way satellites or relatively recent arrivals currently on their first close passage. Measurements of their proper motions, the tiny angular velocities with which they traverse the sky relative to distant background quasars, show that the clouds are moving faster than expected for objects that have been bound to the Milky Way for a Hubble time. Some orbital integrations suggest they are on a first-in-fall trajectory, arriving from the intergalactic environment within the last few billion years. If so, the Magellanic Stream is not the product of billions of years of continuous tidal stripping, but a relatively recent event, and the clouds themselves will make only a brief passage before departing or being fully absorbed. The debate is ongoing, and measurements from future astrometric missions may resolve it. Third in size among local group galaxies is Messier 33, the Triangulum galaxy in the constellation of the same name. MIP3T is the most distant object routinely visible to the unaided eye under ideal dark sky conditions, sitting roughly 2.7 million light-years away. It is a pure spiral galaxy with no bar and a very small bulge. In some respects, a cleaner specimen of the spiral morphology than either the Milky Way or Andromeda. It contains approximately 40 billion stars. MEF33 hosts X-7, an X-ray binary system containing one of the most massive stellar mass black holes directly measured through orbital dynamics, a black hole of roughly 21 solar masses orbiting a blue supergiant companion of approximately 70 solar masses. The measurement was made by tracking the companion star's motion through multiple orbits, then applying Kepler's laws in the same way a planet's orbital period reveals the mass of its host star. XZ7 is an eclipsing system, meaning the black hole periodically passes behind the companion star as seen from Earth, producing dips in the X-ray light curve that allow the orbital inclination to be precisely constrained. M33 is not independent of Andromeda. The two galaxies are gravitationally linked, and observations of the outer stellar population of M33 reveal tidal distortions pointing toward M31. Some stellar material has already been transferred. A bridge of stars connecting the two systems extends between them. M33 is in effect falling toward Andromeda on a trajectory that may result in eventual absorption, likely after the Milky Way-Andromeda merger has concluded. Farther out from the Milky Way-Andromeda pair, the local group becomes sparser, the Wolf landmark Melotte galaxy. an irregular dwarf discovered by Max Wolf in 1909, sits near the group's outer boundary in the constellation Cetus, about 3 million light-years away. It is gravitationally perturbed by interactions with another dwarf system, the galaxy PGC 143, whose tidal influence has distorted its outer structure. WLM is notable for its extremely low metallicity. Its stars contain very few heavy elements, making it a window into conditions more typical of the early universe, when most of the heavy elements that now enrich galaxies had not yet been produced. Within the Milky Way's own satellite system, beyond the Magellanic Clouds, lies a diverse collection of dwarf galaxies distributed across the sky. The Sculptor dwarf spheroidal, discovered in 1938, sits at roughly 280,000 light-years from the Sun and is one of the most studied of these faint companions. It contains almost no gas and shows no ongoing star formation, a frozen fossil of an ancient stellar population whose formation history can be read from the color magnitude diagrams of its stars. The Sculptor dwarf is predominantly old, with most stars having formed more than 10 billion years ago, making it older than the disk of the Milky Way itself. The Fornax dwarf spheroidal, at roughly 460,000 light-years, is unusual among Milky Way satellites because it contains 6 globular clusters, a remarkable number for a galaxy of its luminosity. One of these, Fornax 4, sits very close to the galaxy's center and may represent the stripped remnant of a smaller system absorbed by the Fornax dwarf in its own past. Fornax also contains a younger stellar population alongside a dominant old one, implying multiple episodes of star formation separated by billions of years. These episodic star formation histories are a common feature of dwarf, spheroidal galaxies and are not yet fully explained by models. Leo I and Leo II are 2 more dwarf spheroidal satellites of the Milky Way, lying in the constellation Leo at distances of roughly 820,000 and 690,000 light-years respectively. Leo I is one of the most distant known Milky Way satellites and is moving fast enough that some analysis suggests it may be unbound, on an escape trajectory from the Milky Way, rather than a bound orbit. If so, it may have been flung outward by a past interaction with another massive object, possibly the Large Magellanic Cloud. Leo II, by contrast, shows evidence of extended star formation that continued until relatively recently in cosmic terms, having formed stars over a period of several billion years before quenching. The galaxy nearest to the local group's outer boundary, and sometimes considered a transitional object between the local group and the neighboring M81 group, is NGC 3109. It is a Magellanic-type irregular galaxy in the constellation Hydra, lying approximately 4.3 million light-years away. Its velocity with respect to the local group suggests it is expanding away from us along with the Hubble flow rather than gravitationally bound, placing it just beyond the local group's edge. NGC 309 hosts its own satellite companions, the Sextans A and Sextans B dwarf irregular galaxies, which form a small subgroup in the transition zone between bound and unbound systems. Moving further still, just beyond the formal boundary of the local group, lies Centaurus A, properly designated NGC 5128. This is a peculiar galaxy, neither a pure elliptical nor a spiral, but something intermediate, crossed by a prominent dark band of dust that bisects its optical image. The dust band is the remnant of a spiral galaxy absorbed by NGC 5128 relatively recently in cosmic terms, perhaps a billion years ago. The merger is still ongoing in a structural sense. The 2 populations of stars have not fully mixed, and the dust from the absorbed system has not dissipated. Centaurus A is also one of the most powerful radio sources in the sky, the brightest radio galaxy in the southern celestial hemisphere. Its nucleus harbors a black hole of approximately 55 million solar masses, actively accreting and producing jets that are visible in radio, X-ray, and gamma-ray wavelengths. If we could observe the galaxy in radio wavelengths with the sensitivity of the eye, the radio lobes flanking NGC 5112L8 would appear larger than the full moon. The jets extend at least 13,000 light-years from the nucleus before expanding into the lobes. Gamma-ray observations have detected high-energy emission from these jets, produced by electrons accelerated to relativistic speeds in the jet plasma. Directly relevant to understanding Centaurus A is the class of objects called BL-Lacertae objects, or BL-LEX. These are radio galaxies whose jets happen to be pointed nearly directly toward Earth, so that we see the jet end on rather than sideways. Looking directly into a jet dramatically changes its apparent properties. The emission is Doppler boosted, making it appear far more luminous than it would if seen from the side, and variable on short timescales because the emission region is compact and moving toward us at near light speed. The prototype of the class, BL-Lacertae itself, was classified as a variable star for decades before its extragalactic nature was recognized. When viewed from a direction parallel to the jet rather than perpendicular to it, a radio galaxy like Centaurus A would look like a BL-LEG object, and from another angle, with higher accretion, it would look like a quasar. The same physical system produces different observed properties depending solely on the line of sight from which it is viewed. In the direction of the constellation Ursa Major, at a distance of roughly 11.7 million light-years, lies one of the most visually spectacular interacting galaxy pairs in the nearby universe, M81 and M82. M81, also designated NGC 3003-1, is a grand design spiral galaxy, one of the most geometrically regular spiral structures known. Its arms are smooth, clearly defined, and symmetrically disposed around a prominent central bulge. In visible light, it is a textbook example of the SB morphological class. M82, immediately adjacent in the sky, could hardly look more different. It is an irregular galaxy being torn apart by tidal interaction with M81. But it is the interior of M82 that is most remarkable. At its center, a starburst is underway, star formation at a rate roughly 10 times higher than in the Milky Way, driven by the compression of gas caused by M81's gravitational influence over the past several 100 million years. The result is a central concentration of young, massive stars, so dense that their collective supernovae are driving a galactic wind. A continuous outflow of hot gas, dust and cosmic rays erupting from both faces of the disk in two enormous plumes that extend tens of thousands of light-years above and below the galactic plane. These winds are not unique to M82, they appear wherever star formation proceeds at sufficiently intense rates. But M82's proximity, it lies close enough to resolve individual star clusters in high-resolution images, makes it the best-studied starburst galaxy. The filamentary structure of its winds, the chemical composition of the outflowing material, the spatial distribution of the young star clusters driving the burst. All of these can be measured in M82 with a precision impossible for more distant systems. Starburst winds are now understood as a key mechanism by which galaxies transport heavy elements from their interiors into the circumgalactic medium and ultimately into the intergalactic medium. The iron and oxygen formed in starburst supernovae end up in the gas between galaxies, contributing to the slow chemical enrichment of the universe as a whole. The local group itself exists within a larger structure, on scales of tens of millions of light-years. The local group is one small node in a web of galaxies called the Virgo supercluster, centered on the Virgo cluster, a rich galaxy cluster some 50 million light-years away containing thousands of galaxies. The Virgo cluster exerts a gravitational pull on the local group, slightly retarding the cosmic expansion in its direction, a perturbation called the Virgo-centric flow. The Milky Way and Andromeda are moving through the Hubble flow, not purely in the direction predicted by the expansion alone, but with a component toward Virgo that reflects this gravitational attraction. In 2014, a broader analysis of galaxy velocities in the local universe mapped the extent of the supercluster to which the local group belongs. The result was a structure called Laniakea, a Hawaiian word meaning immeasurable heaven, encompassing some 100,000 galaxies spanning roughly 500 million light-years and containing a total mass of approximately 10 to the power of 17 solar masses. The Virgo supercluster is merely one lobe of Laniakea. The local group sits near its outer edge, the center of the structure, the region toward which all the contained galaxies are slowly flowing. A point astronomers have called the Great Attractor lies in the direction of the constellations Centaurus and Norma at a distance of roughly 150 million light-years. It is largely hidden behind the plane of the Milky Way, making it one of the most studied but least seen regions of the nearby universe. Beyond Laniakea, larger structures still exist. The Shapley supercluster, roughly 650 million light-years away, is one of the largest known concentrations of mass in the observable universe. It may be exerting a gravitational influence on the entire local volume, contributing to the Great Attractor signal that first drew astronomers' attention to the region behind the galactic plane. The cosmic web continues at every scale that has been probed, with filaments connecting clusters and superclusters across billions of light-years and voids occupying the spaces between. Our corner of this structure, the local group, embedded in the outer reaches of Laniakea, orbiting slowly toward the Virgo cluster while Andromeda falls toward us, is a quiet region by cosmological standards. There are no active galactic nuclei among the dominant galaxies. There are no ongoing major mergers. The star formation rate in both the Milky Way and Andromeda is modest compared to systems undergoing starbursts or interactions. We sit in a relatively undisturbed backwater of a modest supercluster on the outskirts of the observable universe. It is a peaceful place to have assembled over 4.5 billion years, a world on which beings became curious enough to measure these distances. The universe around us is populated with galaxies in every state of development. Dwarf irregulars like WLM show us what galaxies looked like when the universe was young and metal-poor. Giant ellipticals like IC Luft-Aulon show us the endpoint of aggressive hierarchical merging. Radio galaxies like Alcyonius and 3C236 show us the extraordinary extent of energy released by supermassive black holes. Merging systems show us evolution in real time, and ordinary spirals like the Triangulum, Andromeda, and our own Milky Way show us what the most common large galaxy form looks like in a universe that is neither too young nor too old. The Andromeda galaxy has accompanied human observation for longer than any other extragalactic object. Ancient Babylonian astronomers noted a smudge near the star we now call Merak. Persian astronomer Abd al-Rahman al-Sufi in the 10th century described it as a small cloud in his systematic catalogue of the night sky, completing the first recorded observation specific enough to be matched to a known object. European astronomers rediscovered it independently in the 17th century, and for most of the following 3 centuries it was understood as a nebula, a gas cloud inside the Milky Way. The mythology surrounding Andromeda's name came later, as the constellations were systematically connected to Greek narrative. Andromeda, daughter of the Ethiopian king Cepheus and his queen Cassiopeia, was chained to a sea cliff as sacrifice to the monster Cetus, punishment for her mother's boast that Andromeda's beauty surpassed that of the sea nymphs. Perseus, returning from his encounter with Medusa, saw Andromeda and killed Cetus with Medusa's severed head. All the Principes, Andromeda, Perseus, Cassiopeia, Cepheus, Cetus, even Pegasus were eventually mapped onto constellations. The galaxy that came to carry Andromeda's name sits in the constellation named for her, a coincidence of astronomical and mythological geography that has proven more lasting than either tradition separately. The modern understanding of M31 as an independent stellar system containing hundreds of billions of stars at a distance of millions of light years emerged from two crucial observations. Heber Curtis, working at Lick Observatory in the early 20th century, noticed that novae in the Andromeda Nebula were systematically 10 magnitudes fainter than novae in the Milky Way. Assuming novae have a characteristic peak luminosity, the implied distance was roughly 500,000 light years, already far outside the Milky Way as then understood. Curtis argued against prevailing opinion that spiral nebulae were independent galaxies. His position became known as the island universe hypothesis. Edwin Hubble, using the new 100-inch Hooker telescope at Mount Wilson in 1923, resolved individual stars in the outer regions of Andromeda and identified Cepheid variables. With measured periods and known luminosities, he calculated a distance of about 900,000 light years, slightly short of the modern value, because calibration errors in the Cepheid period luminosity relation had not yet been corrected, but unambiguously placing Andromeda outside the Milky Way. The debate ended. The universe was vast, filled with galaxies, and the Milky Way was one of them. Since Hubble's time, the tools for studying Andromeda have multiplied and sharpened. The Hubble Space Telescope, launched in 1990 and subsequently repaired and upgraded 5 times, has resolved stars in Andromeda's disk, bulge, halo, and globular clusters with a clarity that ground-based telescopes, blurred by atmospheric turbulence, cannot match. The panchromatic Hubble Andromeda Treasury, known as PHAT, imaged roughly a third of M31's disk using 828 separate Hubble pointings, creating a mosaic of over 100 million individually resolved stars. This catalog has been used to measure star formation rates, stellar population ages and metallicities, dust extinction maps, and the three-dimensional structure of the disk with a precision previously available only for the Milky Way's immediate solar neighborhood. The James Webb Space Telescope, which began science operations in 2022, extends this capability into the infrared with a mirror over 6 times the collecting area of Hubble. JWST's near-infrared camera resolves individual old red giant stars in Andromeda's halo, across fields that previously required hundreds of Hubble orbits. Its ability to see through dust that blocks visible light makes it uniquely suited to studying star-forming regions embedded in the dense gas clouds of M31's disk. First, JWST observations of local group galaxies have already revealed stellar population details inaccessible before, and the full program of local group science with JWST spans years of scheduled observations. Looking forward, the Vera C. Rubin Observatory in Chile, a wide-field ground-based survey telescope scheduled to begin operations in the mid-2020s, will conduct the legacy survey of space and time over 10 years, imaging the entire available southern sky to extraordinary depth every few nights. For local group science, this survey will discover new dwarf satellite galaxies around both the Milky Way and Andromeda, detect stellar streams too faint for current surveys, and measure the variability of hundreds of thousands of stars in M31 simultaneously rather than one field at a time. The resulting catalog of variable stars, stellar streams, and faint satellites will transform our understanding of how the local group assembled its current structure. Radio astronomy will contribute its own perspective. The Square Kilometre Array, a multinational radio telescope network being assembled in South Africa and Australia, will achieve sensitivities and angular resolutions in the radio band that exceed current instruments by orders of magnitude. For Andromeda, and the local group, SKA will map the neutral hydrogen distribution in the halos of dwarf galaxies with enough sensitivity to detect the faintest gas streams and bridges. It will measure the rotation curves of satellites too small and distant to study with current radio arrays. Probing the dark matter distribution in the faintest known galaxies, it will detect radio pulsars, rapidly rotating neutron stars in M31's globular clusters, providing dynamical probes of the black holes at their centers. When we look at Andromeda tonight with the naked eye, a faint elongated smudge just to the northwest of the star Merak, we see it not as it is, but as it was. Light travels at approximately 300,000 kilometers per second in vacuum. At 2.537 million light years, the light reaching our eyes left Andromeda before our genus existed. Homo habilis was not yet walking when that light began its journey. The last common ancestor of modern humans and Neanderthals was still in the future, when those photons departed. What Andromeda looks like at this moment, how its spiral arms are configured, whether any of its novae have exploded, what its central region is doing right now is information that will not arrive for another 2.5 million years. This is not a limitation we can engineer around, it is a fundamental constraint of the universe. The speed of light is the speed of causality, and causality means we can only know the past. The more distant the object, the deeper into the past we see. At cosmological distances, billions of light years, we observe galaxies as they existed when the universe was a fraction of its current age. We reconstruct the history of the cosmos not by reading a single object through time, but by reading many objects at many distances. Piecing together an evolutionary sequence from a collection of snapshots, Andromeda sits at the modest end of that distance scale. It is our immediate neighbor. In galactic terms, it is close enough to study in extraordinary detail, to resolve individual stars, measure stellar populations, map the halo, track the double nucleus, weigh the central black hole, detect the satellites. And yet even Andromeda exists at a distance that makes its present condition unknowable to us. We are separated not just by space, but by time. The local group in which we sit, this modest collection of perhaps 80 galaxies, dominated by two spirals scattered across 3 million light years, is our window onto the wider cosmos. By studying it carefully, we learn how galaxies form, evolve, interact, and eventually merge. We learn how dark matter shapes structure, how black holes regulate star formation, how gas cycles between stars and the surrounding medium, how the chemical elements produced in stellar nucleosynthesis enrich generation after generation of new stars. The universe is not a static backdrop, it is a process. Galaxies are not objects but events, long, slow events measured in billions of years, in which matter is assembled, converted, expelled, and reassembled. The Andromeda Galaxy is one chapter in that process, currently in the middle of its story. Its halo is flowing inward. Its disk is forming stars at a measured pace. Its central black hole is quiet now, but has not always been, and will not always be. In 4 billion years, it will begin the most dramatic chapter of its existence. Merger with the Milky Way, the galaxy in which we sit. We will not be here to observe it. What will be here? What form of observation? What kind of mind? What instruments directed at what sky is beyond our capacity to predict. What we can say is that the universe will continue its work regardless. Matter will fall into gravity wells. Gas will cool and collapse. Stars will ignite, exhaust their fuel, and die. The process that began 13.8 billion years ago with the emergence of space, time, matter, and energy from conditions we do not fully understand will continue long after every civilization currently capable of wondering about it has either transformed into something unrecognizable or ended. For now, though, in this moment, the light from Andromeda is reaching us. 2.5 million years of travel, arriving at the eye and the telescope and the spectrograph. It carries information about 1 trillion stars, a supermassive black hole, a gaseous halo spanning 2 million light years. It carries the light of novae that exploded before our species existed, of star-forming regions currently compressed by the gravity of ancient spiral arms, of white dwarfs slowly cooling in globular clusters that formed when the universe was young. All of that distilled into a faint smudge of light in the northern autumn sky, visible without any instrument at all. That is what the Andromeda Galaxy is, and in the dark, on a clear night, far enough from city lights, you can see it with your own eyes. There is one more dimension to this story that deserves its own space. The question of how Andromeda and the Milky Way came to exist at all, and what the universe looked like before galaxies of this kind were possible. The Andromeda Galaxy is approximately 10 to 12 billion years old, has a coherent structure. Its oldest stars found predominantly in its halo and in the most metal-poor globular clusters formed at redshifts greater than 3, meaning they ignited when the universe was less than 2 billion years old, roughly a seventh of its current age. At that era, the universe looked profoundly different from what we observe today. The cosmic web of filaments and voids had just begun to develop sufficient contrast to be discernible. Galaxy clusters, as we know them, did not yet exist. The objects that eventually became today's galaxies were smaller, denser, more irregular, and far more actively forming stars. The epoch from roughly 400,000 years after the Big Bang to the formation of the first stars, a period lasting perhaps 500 million years, is called the Cosmic Dark Ages. During this time, the universe contained no luminous sources. The primordial plasma of the Big Bang had cooled and recombined into neutral hydrogen and helium gas, which is transparent to light but dark in the sense that nothing was producing it. The universe was filled with a smooth, cool, dark fog of hydrogen atoms, slowly developing the small density variations seeded by quantum fluctuations in the inflationary epoch. Those density variations, regions fractionally denser than the average, gradually amplified under gravity. Dark matter, which does not interact electromagnetically and therefore was not subject to the photon pressure that kept ordinary matter smooth, began clustering first, forming the earliest seeds of cosmic structure. Ordinary matter fell into the dark matter potential wells, accumulating in filaments and at their intersections. Eventually, the density in the most compressed regions became high enough for the gas to collapse and fragment into the first stars. These first stars, population 3 stars as astronomers call them, formed from gas that was nearly pure hydrogen and helium, containing none of the heavy elements that were not produced in the Big Bang itself. Without metals, which act as coolants allowing gas to radiate energy and contract to higher densities. The first stars are thought to have been enormously massive, potentially hundreds of solar masses, burning through their hydrogen fuel in a few million years and dying in colossal explosions or collapsing directly to black holes. They produced and dispersed the first heavy elements: carbon, oxygen, silicon, iron. Every atom heavier than beryllium in the body of every living thing on Earth was forged inside a star or in a stellar explosion. And the very first generation of that production occurred in these ancient, massive, short-lived first stars that lit the end of the cosmic dark ages. The second generation of stars, population 2 stars, formed from gas enriched by the deaths of their predecessors, still extremely metal-poor by modern standards, but no longer pristine. These are the stars found in the oldest globular clusters, in the metal-poor halos of galaxies, and in the oldest dwarf spheroidal satellites. They are the most ancient individually distinguishable objects in the observable universe, some of them more than 13 billion years old. When astronomers measure the chemical compositions of old stars in Andromeda's halo or in Sculptor or Fornax, they are reading the record of enrichment from those first explosions, tracing the chemical history of the universe backward to within a few 100 million years of its beginning. the protogalactic objects that eventually became Andromeda assembled through a process called hierarchical structure formation, small objects forming first, then merging into progressively larger systems. The dark matter simulations that best reproduce observed galaxy properties show a universe in which thousands of small dark matter halos, each potentially hosting a small stellar system, merged over billions of years into the halo that now surrounds Andromeda. Many of those progenitor halos have been fully incorporated, their stellar contents mixed into M31's stellar population and their identity erased. Others, the satellite galaxies we still observe today, survived intact because they fell in on orbits that kept them at sufficient distance from the host's disrupting tidal field. This picture of hierarchical assembly is supported by the stellar streams in Andromeda's halo. Each stream is the debris of a progenitor that did not survive. The giant stellar stream, the northern spur, the western shelf. These features preserve the kinematic and chemical memory of systems that were absorbed anywhere from 1 billion to several billion years ago. By reconstructing the properties of the progenitors from the properties of the debris, astronomers are effectively running galaxy formation in reverse, working backward from the current state of M31's halo to reconstruct the merging history that produced it. This reverse archaeology of galactic history is one of the most productive research programs in nearby galaxy astronomy. There is also the question of what drives galaxies to eventually stop forming stars. Andromeda's current star formation rate is estimated at roughly half a solar mass per year. Modest but not negligible, meaning M31 is still an active system. The Milky Way forms stars at a somewhat higher rate, perhaps 1 to 3 solar masses per year. Both rates are far below the peaks. These galaxies reached several billion years ago, when the universe as a whole was forming stars at its maximum rate, a period called cosmic noon, centered around redshift 2 to 3, roughly 10 billion years ago. Since then, the global star formation rate density of the universe has declined by roughly an order of magnitude. The decline is driven by several processes acting simultaneously. Gas supplies diminish as existing gas is converted into stars. Stellar feedback wins and supernovae from existing stars, heats and expels gas from galaxies faster than it can be replenished. AGN feedback, as described earlier, heats the circumgalactic medium and prevents the cooling flows that would otherwise fuel continued star formation. In the most massive galaxies, all of these processes conspire to produce a transition from active blue star-forming systems to passive red quiescent ones. Andromeda and the Milky Way are in a transitional state, still forming stars, but on a downward trajectory that, absent the coming merger-driven starburst, would have continued declining. The merger itself will temporarily reverse this decline. The compression of gas during the first passage and subsequent interactions will drive the merged system into a brief but intense starburst. Then, as that gas is consumed, expelled, and heated by the resulting supernovae and AGN feedback from the merged black holes, the new elliptical galaxy will quench. Its star formation rate will drop towards zero. Over the following billions of years, it will fade from blue to red, its youngest stars dying without replacement, leaving an aging population of lower mass, longer-lived stars that will persist for trillions of years before finally exhausting their fuel. This fate, a large, red, gas-poor elliptical galaxy, slowly aging in the darkness of an accelerating universe, may sound somber. But it is also a completion. The heavy elements forged in all those stars, scattered through all those supernovae and stellar winds into the intergalactic medium, will persist. The atoms dispersed by ancient supernovae in M31's earliest starburst billions of years ago are already distributed across the local group. The atoms scattered in the Milkomeda merger will eventually spread across tens of millions of light years, seeding future generations of galaxies and stars with the chemical raw material of complexity. Whatever comes next in the universe, it will be built partly from what Andromeda and the Milky Way and all the galaxies in their neighborhood have already made. The sky above us, on a clear autumn night, contains this entire history compressed into one image. A faint smudge of ancient light from 2.5 million years away, carrying in it the signatures of 1 trillion stars, the gravitational shadow of 1 billion solar masses of black hole, the chemical record of 10 billion years of stellar life and death. It requires no instrument to find. It requires only darkness, patience, and the knowledge of where to look. Look north of Mirach. Look toward the faint patch in Perseus. Look at what the universe has built and consider that you are part of the same construction.